hanging in there. So I'm giving this talk on behalf of Lorenzo Milani, who's at the University of Pretoria. This research is chiefly the work of an MSc student, Lize Oosthuizen at UP, and they've just asked me to step in just to present this research on their behalf. Collectively, all of the people listed here on the slide are all working as a team currently on trying to understand the timing, the petrogenesis, and the magmatic sulfide potential of the Kunene AMCG complex in southern Angola and Namibia. And we're funded by Anglo-American, by Samira, and also the National Research Foundation in South Africa. So to jump straight into it, the Kunene AMCG complex is Mesoproterozoic in age, between approximately 1.5 and 1.37 billion years old. It's the largest known AMCG complex. This is basically anorthosite, mandrite, charnockite, and granite. The main two components on the map here are the anorthosites in blue and these granites in red. This is all collectively known as the red granite suite. The A component, the anorthosites, are mostly made up of leucotroctolites and leuconorites. These are situated in domains, scattered across the complex. And they range between 1376 and 1438 million years. So there's quite a long time scale of crystallization of these anorthosites of at least 60 million years. But we do have some ages up to 1500 million years situated up here from the anorthosites, which suggests that they were emplaced and crystallized over a time scale of about 120 million years. So this is consistent with the idea that these types of complexes are formed in convergent type tectonic settings. The red granite suite in pink, these have been very well age dated. All this data is now published, and they have coeval ages with the anorthosites. So this whole system is producing both anorthosite and granite. All of the host rocks around these anorthosites and red granites are Paleoproterozoic basement terrains, part of the Hibernian continental arc system with lots of reworking of Neo-Archean aged crust. And there's a bunch of mafic-ultramafic intrusions located around the periphery of the complex, which are the main focus of this talk, which have the potential to host significant magmatic nickel sulfide deposits. And this whole region has been fairly inaccessible. Unfortunately, this area has been ravaged by political infused civil wars for many decades. And only in recent years have we been able to sort of access this area and do some field work and do some bedrock mapping and some age dating of the rocks just to build up a sort of geological foundation of what's going on. So this is it's the largest known AMCG complex on the planet. The surface exposure is about 15,000 square kilometers, but this is a gravity map showing that the complex is actually up to about 42,500 kilometers squared in size. Much of this half of the complex is just covered by Kalahari sedimentary material. So this further increases the exploration potential of the Kunene complex. So to focus in on these peripheral mafic-ultramafic intrusions, they're mostly peridotitic rocks made up of dunites and Hartsbergites and Websterites. There's some pyroxenites. There's also troctolites and norites. They're mostly fairly small scale in size relative to the main complex of anorthosite. They're commonly cumulates. There's no chilled margins. They're usually very coarse-grained and layered magmatic rocks. And they are locally sulfide mineralized as well, with typical monosulfide solution assemblages and also some intermediate assemblages as well. This whole region was explored in the early 90s following the discovery of the Voisey's Bay magmatic sulfide deposit, because that one is also at the margins of the named plutonic suite, one of another very large AMCG complex. So there has been some drilling work around this intrusion on Conquer in southern Angola, and also around this region in the Zebra Mountains. This is the extension of the anorthosite complex into northern Namibia. There's pretty unclear, precise age relations of these intrusions right now. There's this one age published by Wolf in economic geology for this intrusion Ohomaremba down here, This is a Baddeleyite age of 1220, but we're age dating some of these intrusions right now, and we're getting a combination of Mesoproterozoic ages and Paleoproterozoic ages. So there seems to be significant inheritance in some of these intrusions, or they are mostly Paleoproterozoic in age, and it's not proving to be a straightforward age dating story for some of these rocks. So we don't actually know if they're genetically related to the AMCG complex or if they're part of the basement terrains. Some field photos just showing some of these rocks in the field. These are surface outcrops of the Unconquer intrusion. Here you can see some pyroxenites and some blocks of gabbronorite, which have been disaggregated and broken up by injections of more leuconeritic material. Just a close-up of here of the same platform that's shown. These two photos in the middle are from Ombuku South in northern Namibia, just showing some layering in these leucotroctolites. And then again, similar sorts of relationships here, layering of pyroxenites and leucotroctolites at this Ohomaremba intrusion. So the field textures suggest that these are multiply replenished and conduit style environments with sustained high temperature magmatic flow to give rise to these sort of coarse-grained cumulate intrusions. And it's also a very good environment from which you can produce sulfide and then upgrade sulfides and boost their metal tenors. So this talk is focused on using magnetite as a petrogenetic and metallogenetic indicator. It's a major phase in most magmatic, hydrothermal, and sedimentary ore deposits. Crystallizes from both sulfide and silicate liquids at various temperatures. And there's a series of papers about 10 years ago now by Dare and the group at Shikutami, basically showing that you can use the trace element signatures of magnetite to characterize the crystallization environment. So this study, we've basically combined textual observations, photography with in situ mineral chemistry to try to infer the degree of crystal fractionation, melt evolution, and also trying to understand the potential magmatic nickel sulfide potential of these mafic-ultramafic intrusions. So what we did, we initially conducted a petrographic study, just looking at the different textural types of magnetite in the rocks. And then we did some EPMA work, characterizing the major element compositions of the magnetite, and then collected about 50 trace elements, isotopes of the trace element composition of the magnetite, and combined this data to try to understand how this magnetite formed. So there's results here just showing the major element data. On the right here, this is a ternary diagram from Barnes and Roeder, just showing the trivalent cations in magnetite. Most of these magnetites that we analyzed are true magnetite compositions, but there's some extension towards more chromium compositions as well. So this slide just summarizes the different textural types of magnetite that's present in these intrusions. This is a summary of hundreds of petrographic observations, just shown schematically in a series of cartoons. So there's 5 types overall. You've got magmatic magnetite, which is intergrown with sulfide phases and is interpreted as crystallizing from the sulfide liquid. If there's enough oxygen in the sulfide liquid, then you will precipitate some magnetite from it. There's type 2, where you have magnetite, which is present independent of any sulfide. So this is interpreted as crystallizing from an iron-rich silicate liquid. The third type is this magnetite, which is forming as a replacement after chromium spinel or chromite. And then there's this type 4 and type 5. Both of these are related to secondary replacement and to hydrothermal processes. So type 4, you have magnetite, which is basically replacing pyrrhotite. And then you have type 5, where you have magnetite present in these veins, cross-cutting silicate phases. Really. So a combination of just backscattered and reflected light images. This basically shows the same thing with 2 types of magmatic magnetite, one crystallizing from a sulfide liquid, one crystallizing from a silicate liquid. This is the geochemistry. So the 2 first types that crystallize from the sulfide and silicate liquids show a wide range of these elements and also low high field strength elements because of the crystallization of ilmenite. Nickel versus cobalt is the best discriminant to use to characterize type 1, type 2. The type 1 generally has lower cobalt and nickel compared to type 2. This is because it's co-crystallized with the sulfide liquid. So these chalcophile elements are preferentially partitioned into the sulfide and not the magnetite. Two diagrams here just showing vanadium versus chromium and titanium versus chromium. There's different fields plotted here. There's a field showing the monosulfide solution compositions and intermediate solid solution compositions. Most of these type 1 magnetites plot in the monosulfide solution field in both instances. And there's no evidence of any magnetite crystallization in the presence of the more copper-rich residual liquid of the sulfide. The third type is this interpreted to be a high temperature magnetite. This magnetite is forming as a replacement around chromium spinel. This is common at Nambuku North and Nambuku South. There is massive chromite here, present in both lenses and layers. Yeah, this is a fairly common texture in this particular intrusion. These are the multi-element diagrams for this third type of magnetites. You can see that there's variable contents of chalcophile elements and enrichments in tin, nickel, and zinc. So trace element characteristics which are indicative of this replacement process of a chromium spinel by magnetite. And Lorenzo interprets this as something which is happening at magmatic temperatures. And then finally, just these two types, type 4, type 5. With magnetite replacing sulfides or is present as veinlets in highly serpentinized rock types. These guys show strong depletion in aluminium, titanium, and chromium and vanadium compared to the magmatic types of magnetite. And there's peaks in copper in the type 4 magnetite, and this one here, and this is just interpreted as some sulfide being ablated during the analysis. So there's some remnants, chalcopyrite inclusions in some of this magnetite that was analyzed. So just to summarize the geochemistry of these different types of magnetite in these intrusions. So you can discriminate the magmatic and hydrothermal magnetites quite clearly using titanium and also the nickel chromium ratio. Vanadium and titanium is typically more highly concentrated in the magmatic types of magnetite compared to the hydrothermal variants. And this nickel copper ratio is very useful to identify these high temperature magmatic types of magnetite in these intrusions. So there's also a series of bulk geochemical assays with nickel copper PGE data for many of these intrusions that were drilled back in the 1990s and 2000s. On Buku North, this intrusion in northern Namibia shows some of the highest nickel copper PGE tenors, and this is where type 4 magnetite is fairly common. And Lorenzo and Lize did some detailed SEM work on some of these PGM, on some of these sulfides, these type 4 magnetite grains, and identified some secondary PGM phases, palladium rich and platinum rich. So there seems to be a secondary hydrothermal event which has perhaps enriched some of these serpentinized intrusions in platinum group elements. So they're a potential target of mineral exploration in this region. So I think I'm out of time, so I won't go through the conclusions, but thanks very much.
Maybe we should give a space to the next session. It's 4 o'clock, we're already late, but we can find Ben, right? Yes. Then on the poster session. Chat. Tell you about it.